Think we got it going. Maybe we could actually hear the music today. Welcome to the stream, everyone. It is a beautiful, rainy Friday here in Atlanta. My name is Jason. If you don't know me, I am a owner, CEO of a little automation company out of Alabama, which if you don't know where Alabama is, you're probably not from the US. I mean, everyone in the US knows about Alabama, and it's all good. But anyway, I've got about 25 years or so working with automation experience, and most of that is with Siemens technology, but we also have a lot of other stuff. But yeah, my company, Alpha Industrial Technologies, does controls in agriculture, light industrial, does some mechanical OEM work, all sorts of stuff. We are a Ignition Gold certified solution provider. And yeah, probably got like a list of a bunch of stuff that you don't really care about. But today we are hopefully about to have a good weekend. Like, I mean, honestly, I was trying to do this earlier in the day. So if you're watching this and you are abroad and it's like 10 o'clock at night, sorry about that. Like, had some customer issues today we were working on, and I'm just kind of glad that we got it working today, and able to do the live stream today. So not really expecting too many people on live today, but if you are on live, please drop a like on the stream, drop your name in the comment, say hey where you're from. And yeah, normally we have a pretty good international crowd going here because Siemens does have a little bit more of an international flavor to it. It's in the US, it's coming more and more, I will say, but Alan Bradley is definitely the king in the US. Everywhere else, it's Siemens. So yeah, if you're coming in and this is your first time on stream, welcome. We will be talking today about some motors, drives topics. So it's a little bit kind of more laid back, just kind of a little more informational, and that's why I wasn't really pushing too hard for this topic to be on when everybody could get on. But there is definitely going to be a lot of information in this, and so if you're watching it on demand, there is a lot of stuff that we're going to be talking about motors and drives, how to size them, how to kind of think about them in your applications, and yeah, so that's what we're talking about today. And if this is your first time and you're seeing this on demand, welcome to the channel. We've got a lot of different stuff that's going on. Most of it is around automation. We've got live streams, some edited content. You'll hear me talking about some edited content that yeah, kind of about different blocks and things like that. But yeah, click around on the channel if this is your first time here, and yeah, if you like what you see and you'd like to see more, definitely subscribe and yeah, ring that bell. So normally these live streams are earlier in the day on Friday or kind of earlier in the day on Monday so that more people can join in live. But yeah, life happens, especially in automation, in the automation world for sure. But yeah, today we are talking about motors, and I needed to have my description pulled up here for what we were all talking about first. But I guess it was last week on the stream we had one of the people in chat. They were asking about, hey, maybe you can have kind of a full stream about how to size motors, and it got me thinking about. There are a lot of different motors because we talked about on the last stream, kind of talked about some of the motors that are available and how they are a little bit different, and you program them different and you have different options when you're programming them in Portal. And so one of those things that I wanted to do was just kind of go over some of those, and yeah, kind of tool you up for more stuff. So yeah, without further ado, let's get a little bit of sip of water. Cheers. And a sip of not water. It is Friday, right? Definitely not water, but that's warm. I don't want that to be over there. All right, so we are going to start off today by going through and going a little bit about, kind of talking a little bit about some industrial motors, okay? And I'm going to kind of draw a little bit here in paint on down here on this other screen. And again, this is going to be more kind of like a tutorial. A lot of information in here. If you can watch it on demand afterwards, kind of throw this on while you're working through your work. Maybe there's some information here that can help you out in your projects. So, yeah. So let's get down here on the sketch pad, and let's be looking at is that going to work? Okay, so that works there. And yeah, so let's talk about just our standard induction motors. These you'll come across them in a lot of different places, all over. I mean, really anywhere. They're your standard kind of 4-pole. What you'll see is 4-pole induction motors. Okay. And one of the things about these motors is that, sorry, got a little too much on my tiny desk. So most of the time these motors are going to be in industry. You're going to have 3-phase motors, and depending where you are in the world, you are going to be on different voltages, either 480, 230, or maybe if you're in some high horsepower applications, you might even be doing some like 690 volts, or even some medium voltage stuff like 12470 volt motors. But they kind of all are based off of some similar principles that kind of go a long way. Okay, and we're going to talk about these basic principles just really quick. And again, this is not going to be very exhaustive because I don't want to go too long on all this stuff. But if you want to know a little bit more about these types of kind of like basic motor stuff, just comment down below on this video, and we'll do some more of this kind of like basic sort of stuff, because I know everywhere, no matter where you are in your journey, in your automation journey, if you're just starting out, or even if have been doing it for years, some of this information we're going to be talking about today is going to be very helpful. Some of it might not be as useful until you're a little bit more advanced, but some of it might be the first time that you're seeing it, and it just kind of clicks. But so 3-phase induction motors, you have obviously 3-phase power. And so 3-phase power is really based off of the fact that is how most of our power is generated. So most of our power throughout all time, even in like nuclear power plants, it's still, you are just boiling water. Unless you are in a solar plant or a windmill, you're pretty much going to be boiling water and making steam and turning some sort of piston fan, turbine. There we go. That's the word. Did I say it was a long day today? Yeah, it's been a long day. So you're going to burn energy, and it's going to turn a turbine and essentially run an electric motor in reverse. So you're going to attach to an electric motor, and because you are spinning the electric motor, it will be generating power. So there's a couple of terms that we're going to talk about. If you are physically doing work to turn the electric motor, then it is going to be in a generator, okay? If you are taking power from like the grid, and these are out onto the grid, and you're pulling power off of that grid and turning your motor, that's gonna be motoring. So generating and motoring, you'll see those terms kind of talked about today. And yeah, so just know that the reason that's three-phase power is because most power generation from all time is just spinning a big motor, and a big three-phase motor, and it creating the grid. So keep that in mind. So the cool thing about these blah. So let's go through and clear out this. So a very simplistic way of thinking about a motor is if we have a coil of wire, or I guess we have a couple of coils of wire, okay? And if we run a current through this coils of wire, just your basic principles of electricity, you run current in through this, it will create a magnetic field, okay? And in this case, if this was looped around like this and we were running through this coils of wire, this would generate a magnetic field that would kind of look like this. Okay, so we have our general magnetic field like that, and so that's kind of what our magnetic field would look like between these two coils. So just know that this would be very similar to the magnetic field that a magnet, the north and a south pole, okay, would generate. Same kind of principle. Okay, so this is basic motor 101 type stuff. So this is the coils over here, coils of wire, and this is an actual permanent magnet, okay? So the easiest way to think about what a motor is doing is, I'm going to clear all this out, and you take a couple of coils of wire, like we have there, and you put a magnet in the middle of it, okay? All right, well, and when you activate this, the magnetic field is going to be in this direction, and these magnetic fields will want to align. Basic, really simple stuff, but so this will want to move like this in order for those magnetic fields to get into alignment. And so if this was on a bearing, if this magnet was on a bearing, then it would rotate and whoop, and align up and stop, okay? Because if we had a fixed current going through this would be a fixed magnetic field, and then it would align just like putting two magnets together. They'd boop, align, and then they would stop moving like that. Well, obviously, that was pretty good for a minute, for a second or so. As it aligned, we had our motion. So what we could do is, if we had some form of, to where maybe we had a second set of coils like this, okay? Then there would be a magnetic field alignment like this, right? And again, this is a very, very rudimentary way of thinking about this. And maybe what we could do is time it to where, just as this is getting aligned up with this, we shut this magnetic field off, we break that, and turn this magnetic field on. And so now, as this rotor, as this magnet pulls all the way through, it's like, oh, hey, I don't have a magnetic field anymore. I want to now align my magnetic field, continue on down to this way. And then we could say, all right, let's turn this one off and reverse the rotation or reverse the direction of these coils and make it to where the north would want to align this way. And then obviously it would want to continue on around. And if we continue this kind of pattern of kind of turning on and off these coils of wire, you would then get this kind of continuous motion. Okay, so it would be jumping from pole to pole to pole. Okay, so that's one way of kind of thinking about a very basic motor, because that is the principles of what's going on in this motor. Okay, so I'm going to clear out this, and again, if you're watching this on demand or live in chat, and you have a question, feel free to drop it. And if you're on demand, I'll try to get back with you to answer. Like, no question is a bad question. Wherever you are in your automation journey is a great place to be, because frankly, it's the only place you can be. And yeah, it's where you want to go. So ask those questions if you have questions, but this is the basic principle of electric motors. So let's clear this out. And a little term that we have is we will have a magnetic field, and then kind of our secondary magnetic field. Okay. And again, these are rotating. It's constantly rotating because that's how you make this motion. Okay. In an induction motor, the cool thing, what we just drew was actually how a DC motor essentially works. You have a magnet on a rotor and you're aligning these fields. If you want better torque control, if you want better resolution, you put more magnets, you put more poles. Okay, so what you can do with an AC motor, because with a magnetic field from a DC current source is going to be fixed, right? Because voltage is same, resistance same, current is the same. So you throw on 500 volts DC and it outputs it. And so you have to use, on a DC motor, you have to use what is called brushes, because you have to turn on and off those circuits. We're not going to talk about those because honestly, those type of motors, because of those brushes, are like insanely time consuming to keep up, and they are kind of going away. There's still definitely some applications where you're going to see them, but we're going to be talking about AC motors. Cool thing about an AC voltage is if this is 0, it will alternate, right? AC, alternating current, like that is literally what the whole thing is. So your voltage is constantly changing, which sounds pretty cool, because if you take and you're constantly changing in a coil of wire, right? The intensity of that magnetic field will be getting bigger and then getting smaller and going negative. Because remember, we wanted to flip the polarity of this at one point, right? So right here, the voltage is flipping negative. Here, it's going from negative to positive. So AC voltage automatically, and AC current, I should say, AC current automatically gives us the ability to kind of do all of the switching, because it's built into the system itself. So without getting into too much more detail, what you end up doing is you have the rotation of the field in the rotor or the shaft, okay? Because inside a motor, you're going to have a shaft and then some windings or maybe some magnets or something inside. And then you're going to have the stator on the outside. So rotor, stator stays, rotor rotates. Nice and simple. Simple enough for me to understand. So the cool thing about this kind of oscillating voltage is it creates automatically a field that will go from like kind of highly positive in this direction to a little less positive, and then it'll invert and then get like this, and then go like this, and then go down, and then invert. Okay? So that's kind of what's going on just between these two poles of our what's it called? Our motor, right? So our coils of wire. So it creates this kind of sinusoidal signal, right? All right. So I'm scribbling all over this place, but what we have is we have this, our rotor will try to follow this signal. In a three-phase motor, what you can think is we have one coil here, and we'll put another coil here. But because we have three phases, each phase will be slightly out of phase of each other. And so it'll create a signal like this. So instead of a single phase to where we only have one voltage going up and down, we have three phase. And how this is getting, what's up, Thomas? Good to see you. Hey, I am actually the one that is really late today, so don't worry about being late. It's just great to see you. We're talking about motors, trying not to get too off into the weeds in this, but just a little bit of understanding about how a motor works before we start talking about different types of motors. So every motor is going to create one magnetic field, that this big magnetic field that's created by the stator is rotating, okay? And then the rotating portion is also going to have a magnetic field that is constantly trying to align and kind of run behind the other magnetic field. So there's two types of motors. At their core, there are synchronous, and that is an O, synchronous. I don't even know if that's spelled right. And then asynchronous. Okay, so which asynchronous means that the rotor magnetic field should never catch the stator magnetic field. So the magnetic field that's created by this guy is never caught by the magnetic field that is on the rotor itself. Okay, so that's asynchronous. They're always out of sync, because otherwise, a rule in asynchronous motors is there has to be slip. And this comes up in what we're about to talk about here, is if your rotor, if your shaft is moving at the same RPM as your magnetic field, so the same number of cycles per minute, then on an asynchronous motor, you have zero torque. So it just kind of wants to flop back and forth. It doesn't have the ability to speed up or slow down. And we're going to talk about this on a torque curve here in a second. Well, in a synchronous motor, you lock it in, and then that's how you actually generate torque. Most of the time, you are going to be using asynchronous motors. So we're only going to be talking about this, or asynchronous motors today for the most part, just because, I mean, a drive kind of takes stuff out. And we're talking about how motors really interact with drives. So this is our basic principle. You have a magnetic field, and that's rotating around in the stator. And then you have the actual shaft that is rotating at a different speed than the magnetic field that is in the stator. Okay, so this term right here, the number of degrees is slip. Okay, just like you're trying to spin and it slips in your hand. That's what it means. So like if you're trying to turn a wrench or turn a screwdriver and it's slipping in your hand, same principle. Because if you are running at 100 RPM, or I guess this is in the US, this is 60 cycles per second. Elsewhere, it's going to be 50. If you're really unlucky, you have no idea, because it could be anything. It could be 49, it could be 63, it could be 55. And in those cases, you have a lot of problems because of what we're about to talk about. So let's clear this off. And so you have to have slip. And so I'm going to draw a little graph, okay? And this is on the x-axis. This is rotor speed. Okay, so that's the actual shaft. This guy, right? So that's this guy's speed. So actually how fast your motor is turning. Okay, and versus how fast the magnetic field is turning. Okay, except for this first graph, we are going to be talking about a fixed frequency. Okay, so in the US, we're going to be talking about 60 hertz, and then elsewhere 50 hertz or whatever. So that's what we're talking about. If you take a 3-phase voltage and hook it up here, well, first of all, this motor won't run, but we'll talk about why here in a second. But to an induction motor, you throw it what's called across the line. You just throw power, 3-phase power onto it. You are putting either 50 or 60 hertz onto that motor. And so that means that the stator, the actual stator magnetic field, is rotating at a constant frequency. So what happens is your motor goes from 0 speed, sitting like this, and it starts to speed up, right? It starts to speed up. Well, what this looks like, so is as we go along this line, we're going to be speeding up, right? So the torque that is available to you is very important in a standard induction motor. So like a 4-pole induction motor would look essentially like this, right? So it's got 1, 2, 3, 4. So it has 2 pairs. And so you have these loops of wires that kind of look like this inside, right? Okay. So we're going to get rid of all that. So that's a 4-pole standard induction motor. And when you throw the power on in the US, I'm gonna talk in US because it's 60 hertz. So this would be 60 hertz. Okay. And as this motor starts to speed up, you will see that this is going to be the torque, T-O-R-Q-U-E, and also is going to be the current because they're directly related. Okay, so on the y-axis is going to be the motor current or the motor torque. And so what you'll see is it'll start out and you will lose some motor speed or motor torque available to you, right? And then you will go, it'll spike up like this. And then when it goes here, it goes down to 0, right? So what you have is this kind of like what's called a saddle here. So as you start accelerating, if you cannot accelerate through this saddle, you will stall, because the amount of torque required to accelerate is more than the motor and that magnetic field can generate, okay? So obviously, right here is going to be your peak torque, and it is somewhere that is not at 60 hertz. Let's say this is 45 hertz. I really don't know what these numbers actually are. They don't really matter. Just know that it's not 60 hertz. Because remember, in an asynchronous motor, we have to have slip. So if the rotor speed equals 60 hertz in the US, then that means it's not going to be able to generate any torque. So unless there's no friction or no load on it, it's basically just going to run at 60 hertz, and it's just going to kind of be like a wet noodle. But the second you either speed up, which how can you speed up, or slow down, like I'm clamping down on it, trying to hold it back, I'm going to be slowing that down. And so that motor speed will start to come back, and then you notice, my torque and my current starts to go up. So we start generating torque in order to try and move it back to the 60 hertz. So moves it up to 60 hertz, it speeds it up, and then it slows down. Speeds up, slows down. That's kind of what's going on. Well, the way these induction motors are actually rated for across the line, very important. Remember, this is across the line. This is like throwing a switch and throwing this motor on, and here's how it's going to accelerate. If you put too much load down onto it and you start slowing it down, there's going to be what's called this is the breakover torque. Okay? So once you get up this is the maximum torque that you have available. And if you start to really like hammer down on that motor, and it really starts to slow down, once it gets to this point, if it slows down any further and the load doesn't change, guess what? You're going straight to 0. And so you're stalling your motor. So that's what this torque curve looks like. Throw it across the line, it starts to speed up, it goes, and then somewhere along this curve, there will be a peak torque. Well, where are motors rated? Do they rate them at the peak? Do they rate them at the bottom? What do they rate them at? Well, they have what's called a rated slip, which is the distance between rated slip. So remember, that's the difference between the rated frequency and the rated actual RPM. So you'll notice on these like induction motors, it's rated at 60 hertz, 50 hertz, whatever. And then the motor itself has an RPM rating. Well, a 4-pole motor is always going to, at 60 hertz, I should say, generate the speed at synchronous speed is going to be 1800 RPM. On a 50 hertz, that's going to be what? 1500 RPM, right? And so, and that's just based off of an equation, and you have different motor designs, which we'll talk about here in a second, that will change that number. So the more poles, the slower you go, but the more torque you have. So we'll talk about that in a second. But just know that you have a rated speed, a rated frequency, and a rated slip. Most of the time, what you get is the horsepower or kilowatt rating, for all you metric people, is going to be the amount of power available, so the current times the speed, that's going to be the actual power, so the kW or horsepower rating is going to be rated at the rated speed. So this would be 1800 RPM. This is going to be the rated speed. On a decent size motor, this is going to be 1775. On a smaller motor, it might be 1750. Or like for you 50 hertz people, that might be like a 1400 RPM or like a 1350 RPM. But depending on how efficient the motor is, these numbers will change. So you need to make sure that you notice, like when you are looking at this kind of these ratings, like, oh, this is a 10 horsepower motor, this is a 7.5 kW motor. You need to know that power is not at the 1800, 1500 RPM. It's going to be at some slower speed. So don't get in trouble if you are expecting it to run at 1800 or 1500 RPM, because it will not run. That style of motor across the line, and I'm going to keep bringing that up, across the line will not run at 1800 RPM. It will not generate that torque at that speed. So that right there can get you into trouble. If you're expecting it to run at 1800 RPM and you're doing all your math of like your process and everything, then you're going to be getting in trouble. So, but drives can get you out of trouble, right? So that's what we're going to talk about here in a second. Looks like we got a couple more people coming on. Welcome to the stream. Like, if this is your first time on the stream, drop it in chat where you're from. Actually, if you're not, if this isn't your first time on stream, drop in chat. And like, if you want to learn more about motors, like the stream, get it out there. Like, get it out to people that are nerds like me, that want to, on a Friday night, sit and talk about motors, because we all know that motors drive the world. And on that, I'm taking a drink of water. And then maybe a drink of not water. Yes, we are. Lucid. It's okay. It's okay. We have a club. Which, by the way, Lucid, grounding. Let's talk about grounding. Yeah. Anyway, no, we're not going to talk about grounding because I have trauma about grounding right now. But grounding is very important in drive systems, and we might talk about it here in a second. But let's continue on talking about motors, because we are looking at this 4-pole type of motor. Now, awesome, turkey, that's awesome. Which, by the way, I was in Istanbul for like a layover for a flight, and that is some of the best food I've had. Like, I freaking love Turkish food. my wife doesn't like the heavy meats and everything, and so I don't get to eat it nearly as much as I would like, but I absolutely love Turkish food. I don't know about anybody else in here, but motors, we're gonna talk about motors. So with this whole thing, that's our first kind of design metric of how do we, like, what speed do we want our system to be running at, okay? And that's a pretty kind of optimized sort of thing, because it's like, what can you do if you're running across the line? If you're running across the line and you need more speed, it's called a gear ratio. You could do a large to small gear ratio, like on a pulley. But what happens if you do that? Well, you reduce your you reduce the overall, or I guess you reduce the torque available to you. So you increase the power requirement. So the cool thing about a power requirement is that power is actually equal through a gear ratio, minus a little bit of losses for bearings and stuff. But for the most part, if a load is going to require 10 kW of power, that you can get a 10 kW motor and then move to a different speed and different ratio, because a actual power is based on speed and torque. So if you have like a 2000 RPM rated process and it requires 10 Newton meters of torque, then that is going to be a certain amount of power. Now, the torque available at a lower end of the same power. So if you have something that runs slower, say you're wanting to run 2000 RPM and you were running at 1800, or in this case 1750 RPM, then that, say it's 10 kW of power, it's still, there's going to be more torque in a 10 kW motor running 1750 than a 2000 RPM process that is still running 10 kW. There's going to be less torque required in order to generate that speed because you're running faster. Okay, so remember, torque, speed, you increase more torque, it's going to increase your power. If you have fixed power, then if you increase your speed, it's decreasing your torque. Okay, so think about that. So we might talk about that in like how to actually come up with those torque numbers later, but I doubt that I have the energy for that tonight. But so cool thing about this little setup here is we have an across the line thing that we have going here that sorry, I need to mute all my tabs because I get distracted. But all right, so we have our this is across the line. Now, most of the time, here's a cool thing that, like, earlier in the stream, I talked about how no matter where you are in your automation journey, you can learn something. Well, I didn't really capture this into my brain until I was helping my dad write his series of books about automation. And we kind of stumbled across this fact that, like, what I'm about to show you is like, wait a second, that's why that does this. Because you remember I talked about how most power plants run a just an electric motor, and you run steam and it turns a turbine and it creates electricity, right? Well, we knew that if you hook this up to a drive and you start kind of trying to slow the process down, it generates power. But we never really understood why. Because one of the things, though, is this torque curve, I kind of cheated and I only drew half of it. So this is at 60 hertz, but guess what? Your rotor speed can absolutely go faster than 60 hertz. And you might say, how in the world could I do that? Well, that would be in the case of like a water wheel. The water wheel, if you take and put a big water wheel in a stream and it's sitting there turning, and you put a pulley to where it turns the shaft at 2000 RPM. Okay? Well, 2000 RPM is somewhere up here. What does the torque look like then? Well, it's actually, we just mirror this across this axis. So it just mirrors and kind of does the exact same thing, except in the opposite direction. So now this is positive torque, right? So that's motoring torque. And this is minus. So this is generating torque. Okay? So that right there is in and of itself pretty stinking cool. So if we start driving an induction motor faster than 60 hertz, it will start generating once there's a magnetic field in there. We don't have to, there's starting capacitors, voltages, blah, 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 all that stuff. You don't need to worry about that. Once it gets going, if you start driving the load faster than its 1800 RPM, or for a 4-pole motor on 60 hertz, it will actually start to generate torque. So if you are outrunning your frequency, if you're outrunning your line frequency, it is putting power backwards because this is a negative torque. So it's putting negative current. So it's going back into the line. And that's what sometimes you'll call a regenerative load, a generating load. But that is how power is done. It starts up a magnetic field in one direction, and then it starts fighting against it, and it starts generating power, which is kind of stinking cool. It's a little bit, it's like bootstrapping yourself, right? It's a little bit hard to think about. And honestly, most of these like perpetual motion machines that are out there about like different voltages and like pulleys and like all this different stuff, it's this. This is it doesn't actually generate any energy. The only way it's really able to do anything is because of these kind of concepts of that we're kind of talking about. So just remember that if we drive something faster, this once the rotor speed gets like, it is always trying to run at that base speed, 60 hertz, whatever that is, 50 hertz. It is always trying to run at that rated frequency. So if it starts running at 67 hertz out here, it will start to try and go back the other direction. And you can get this same type of setup to where what happens if you go too far, too fast that way. I think there's a song in the US, and it kind of goes, "Ooh, Janie was a runaway," and you never want to have a runaway of an industrial motor, because once it starts to run away, you can't stop it. And I'm very sorry for the American Idol thing there. But I'm an engineer, not an artist. But yeah, so if you start to power or you start to spin it faster, you will lose negative torque, and it'll eventually go to zero torque and just run away and just fall downhill. So same principle, that there's only so much work that a motor can do, and that is the power rating. Power rating. Okay? So there's only so much torque that it can do. And so just remember that. So this is across the line. This is kind of your basic. You can do this, maybe not in your backyard, because if you have 3-phase power in your backyard, that's pretty cool. I would want to hang out in your backyard. But we don't all use just starters here. We are fancy. We are high tech, right? And so let's talk about how a drive handles the same motor, same physical motor, same copper, same everything, same ratings. Okay. Now, everybody, you might or might not know that there are inverter duty motors, and that is very important if you are going to run a motor on a drive. make sure that it is rated for being run on a drive, because we're not going to talk about it. We're not going to talk about it now, I don't think, but you definitely need to have inverter duty motors on any motor that you're trying to run, because otherwise it will not last very long at all. You will start having ground faults in that motor pretty quickly, because inverter duty, the main thing is the insulation on the windings, and it's kind of a bit of black magic at this point that we might talk about on some other time. But just make sure, first thing, if you're gonna run it on a drive, make sure it's inverter duty motor. Okay, and so these are going to be like in the US, like your Black Max, Baldor motors, things like that. I mean, all SIMOTICS motors are designed to be driven by drive. So Siemens, GP, SD, all of those are inverter duty. But you can absolutely get into, in the US, they'll call these like farm duty rated motors, that you put one of those on a drive. And it'll last who knows how long, but it's not going to last nearly as long as it would if it was across the line. So the thing about a drive, and we'll talk about the thing about a drive, okay, is that torque curve that we just had. That torque curve was available. It looked the way it looked because the line was 60 or 50 hertz. Okay, so the line as seen by the motor. All right, remember that. So in our across the line, there's nothing messing with the line frequency. The frequency is what it is coming in. You throw the switch, bam, it goes across the line. Well, in a drive actually modifies what the motor sees as its frequency, its line frequency. Okay, and kind of let that simmer in, because you're like, oh, of course, it's a VFD, variable frequency drive. Yeah, that's what it means. But instead of this kind of curve that we drew just a second ago, like that, right? This was at 60 hertz, right? Well, what does this curve look like at 50 hertz if we graphed it on the same thing? Well, it would look kind of like this. Like that. Well, what would it look like at 70 hertz? Like that. What would it look like at, and insert frequency here? You would see that every one, there is essentially, it creates at every frequency, it changes and creates basically a wall. Now that's kind of complicated, to say the least, right? Well, what that means is at 60 hertz, this motor is rated for this much torque, right? Well, across the line, it would not be able to run at this much torque right here, right? Because this is where it would be on that 60 hertz curve. Well, if we lowered our frequency down on the line to right here, yeah, we would, right? So that's kind of the point. So all of a sudden, this torque curve, what a drive does is it gives you the ability to have rated torque throughout the entire speed range of the drive, or of the motor, I should say. Kind of cool. And if you notice, hey, technically there's this peak torque up here, right? Guess what? We could kind of fiddle around with that if we really wanted to. Thank you so much, Sergey. Welcome to the stream. Hello from Spain. Hello from, I mean, I'm in Atlanta, but yeah, the US. Welcome to the stream. I appreciate the kind words, and I appreciate that there are other people on this planet that find these videos interesting. Because, yeah, we're a special breed. But yeah, so the cool thing about a drive, because it can modify this frequency, is it can make a 10 horsepower, sorry for the Imperial units, the Freedom units, a 10 horsepower motor. It can give, so rated, I don't even know what this number would be. Say it's, all right, I'm going to immediately go back on, because I don't like using foot pounds. So a 10 kW motor that is rated, that has 10 Newton meters, okay, of torque, then it will be able to have 10 Newton meters available from 0 to whatever the rated speed is. Okay, so, and I'll put an asterisk there because we're about to talk about that asterisk. So a drive gives you this crazy ability to be able to extend this torque range to where you can definitely prevent stalling. If you were running down here, this 30 hertz, and you had a load at 30 hertz that required whatever this torque is, say this is 10 Newton meters, it would stall if you were running this across the line, 100%. And so the only way you would be able to run that motor across the line is if you moved this curve right here up to this point. And what does that mean? A bigger motor. So you're having to upsize entirely into a new motor because your process needs to run at a slower speed. And that just means that it's broken over. There's all these problems. But you put a drive on it, and then all of a sudden that, say it's a 10 kW motor, all of a sudden that 10 kW motor all of a sudden works down at 30 hertz, and it has plenty of torque. And so it's magic. But it's based on this whole rotating magnetic fields. Super cool, super, like, I guess, like, really understanding this takes just a long time. And this little part right here that I'm showing you right here really didn't sink in until I was probably, I don't know, in my 30s. And so it's like after 18, 19 years of experience, I knew how to use this stuff, but really understanding it, I didn't quite get it. And there's another little thing that the drive is doing to be able to kind of like do this, but you don't really need to know. It's called the volts per hertz curve. And so, like, in order to provide the same amount of torque, it's actually lowering the voltage once it gets down lower speed in order to provide that consistent torque, because otherwise your power is kind of going to be the same. And so it's like all over the place. So there's some other stuff that a drive's doing, but just know that on a drive, your kW rating, or your power rating, horsepower, kilowatt rating, is rated at some call it base speed or rated frequency or whatever. That is the torque at that speed. And so that's going to be the power, okay? Because it's going to be a fixed voltage, okay? With a drive, you can take that torque and say, okay, 10 kW at 1400 RPM. That, do my math, that gives me 10 Newton meters. And then I can say, okay, I can run any speed, no matter what, up to that rated speed at 10 Newton meters. Okay, so that's where you can do that from there. And you say, hey, I can go faster. I can go 70 hertz. And you're absolutely right. The problem is, because of that voltage, you can only get that top tier, that the torque is based on speed and voltage. Well, you can't increase your voltage anymore. All right. And so as you increase your speed, your power is going to be constant. And you remember what we talked about. If you're running faster, then your power is the same, then your torque is going to be lower. So keep that in mind. That's called running in what's called field weakening mode. And the crazy thing about it is, like, that's an old DC motor term. In order to run over a certain speed, you had to weaken the field. But just know that if you go over 60 hertz on a rated 60 hertz motor, if you go over that RPM, you are going to lose torque as calculated here. But 0 up to that speed, you're good to go. So, drives are pretty cool, wouldn't you say? I hope everybody's got some cool stuff going for the weekend. Because, yeah, it's getting into spring, or it's starting to when was spring? Spring was like 2 days ago? That's like the first of spring. So yeah, it's officially spring, and it's like 0 C here. Actually, it's like 29 degrees Fahrenheit. So that's like negative C, and that's in the south. That's like crazy. So focus. Sorry. We're talking about now. I want to talk about the fact that why I put this little asterisk here. Okay? Because now we're going to go into different types of motors. I'm going to clear this. So most induction motors or industrial motors that you are going to see out on your plant floor, out in industry, anywhere like that, are going to be what's called totally enclosed fan cooled, TEFC. Okay, so totally, I'm not spelling that right. Enclosed fan cooled. I'm trying to think if I have one of those laying around here. I do not believe I do. Because this guy is not. This is not a totally enclosed fan cool. We'll talk about that in a second. And I'm not going to just like toss this over my shoulder because this is freaking heavy. So TEFC, totally enclosed fan cool. What this is you have the body of the motor, have your little shaft like this, feet, maybe. But on the back, you have connected to the back end of the shaft, you have a fan. Now, this little fan might have a little cover over it because it's totally enclosed. And so you might have this kind of like shield guarding over it that's like attached. But there's a fan that is either pulling air this way, or it's trying to pull air across the body. Okay, so depending on the way your motor is designed, it might have like ribs, and then but this is a TEFC motor, and so this thing is spinning and pulling in motor or air like this and blowing it on into the windings and onto the motor in order to cool it. And cooling is important because we're going to talk in a later about I squared C, or I guess I squared T is probably what we need to undo. Forget about that. I squared T. So the current times time of heating up something. So this is going to be very important. So the more current, the more heat that is going to be produced. The longer you are there, the more heat is going to be produced. But it's kind of important. It's a square, right? So thing about it is you got to get the heat out. Otherwise, you're going to burn up your motor. Everyone's seen like windings get burned up and damaged. The insulation breaks down. And these motors, depending on how hot the motor will get, you will have different insulation class of the winding itself. So you'll have like class F, class H, class G, things like that. And so that's the temperature that it can heat up. So a higher class, the less cooling it needs to have. And that should cue into something in your mind, the fact that these motors are really sensitive to temperature. Electronics are really sensitive to temperature. And this square right here, this is your heat. Okay? That square means it can get really hot. So one of the things about a TEFC motor is, what is this fan attached to? This guy right here, right? The shaft. So the way that a TEFC motor is rated is that it can run continuous duty, or what is S1, continuous duty at base speed. So our rated speed, it can run indefinitely at base speed. So, and the reason that is this fan is designed to blow enough air to cool the current buildup, the heat buildup at base current, base load. So that 10 kW is going to produce so much heat, and that 10 kW is rated at 50 hertz, 60 hertz, and that means that fan is going to be turning at that speed. So that's 1750 or 1400 RPM, 1350 RPM. So whatever that is, it's going to be running at that. And so everybody knows that airflow, well, everybody probably, you should know that airflow in a fan is also a square. It's a square law as well. So the airflow coming off of a fan is proportional by the square. So the slower you go, the much less cooling you get. And that really should worry you when you start talking about running a standard motor on a drive, because you might think, oh, hey, I'm going to run this at 20 hertz, or 100 RPM all day long, and I'm going to load it down because Jason Watts told me that a drive can run a 10 kW motor at 20 hertz all day because the drive can put out that torque. And it will burn up. Absolutely burn up. Because this fan is not turning. The airflow is a square law as well. And so you have the same amount of heat build up because it's the same amount of current, the same amount of torque, but you have much less cooling. So enter in a rule of thumb. Motor manufacturers, most decent motor manufacturers are going to have at around a 4 or 5 to 1 what they call turn down ratio. And that means that you can run on a 4-to-1 turn down. You can run at 1/4 the rated speed. On a 5-to-1 turn down, you can run at 1/5 the rated speed. Okay, so that's very, very important. Welcome from Yemen. It is great to see such a good international crowd here. Again, Siemens is, if you are not familiar with Siemens, Siemens is international. It is the world's largest automation manufacturer, and it is cool. If this is the first time on your stream, be sure to say hey, and look at my channel and look at the other videos that's on it and see if it's helpful to you. And if it is, be sure to subscribe. Like this stream if you're on here right now, at least, because that might get it out to somebody that's just bumming through YouTube on this Friday night and want to learn some cool stuff about motors. So, cool thing. I'm going to give Siemens a little bit of a plug here. Siemens motors are generally rated at a higher turn down ratio, so like they can run slower on their electronic, or not electronics, but on their motors. So there is a motor that I absolutely love, but they are expensive. But you buy one of them and forget about it. And they are the SD100 IEEE 841 motors. If you have an application that you want to run for a long time, look at the IEEE 841 motors by Siemens SD100s. They are stinking good. And by the way, I'm not sponsored by Siemens. I'm just like a Siemens fanboy because I love doing things once and then not having to come back and do them. And when I was an application engineer for a Siemens distributor, I would have I guess customers that had other manufacturers' equipment in there, shall be named unnamed, and they would get mad at me because they didn't know how to use the equipment and program the Siemens equipment. And every time that thing went down, they didn't know how to work on it. And I'd be like, well, what else is in your plan? And they would name this other manufacturer, and you're like, yeah, we've got to work. We work on those all the time, so we know how to use those, but we don't know how to use the Siemens stuff. And I'm like, wouldn't you want to not have to work on something all the time? Isn't that a good thing? So, but anyway, so that's why I love Siemens, because we're going to talk here in a minute about the kind of the drive ratings and things, and we're talking about heat, and this is kind of introduction to heat, because heat in a drive system, heat in motors, heat in drives, it's your enemy. That's what you're fighting against, because this current torque, really everything is rated. It doesn't matter the manufacturer. It doesn't matter who's doing it, what country, where you are, what planet. Even in space, everything is rated off of heat. And if you can't get the heat out of the motor, then your rating is no good. And so, like, for real, honestly, the like in space, everyone talks about how like hot it is, or sorry, how cold it is. Most of the electronics, there's no way for the heat to get off of the electronics. And so, like, if you generate any heat, we take for granted the fact that, like, oh, hey, we're going to put a fan and like an intercooler on our GPU and blow heat off of our GPU. You can't do that in space because there's no air. Anyway, tangent. But we're fighting heat today, and the thing about it is, like, there are a lot of manufacturers. Everybody does it. They have their different naming game and rating game, and one of the things that you need to do if you are specifying a system is to make sure that you are comparing apples to apples. Because here in a minute, I'm going to show you how things might seem the same, but they're really not. Because if you rate at different speeds, if you rate at different temperatures, if you rate over different duty cycles, which we will talk about here in a second, it makes a huge world of difference in how much headache you have at your plant. So we've got this fan, and this is a TEFC motor that is got a fan hooked onto the shaft. Well, you're like, well, what if I just take, and instead of have this connected to a shaft, what if I put a little motor right here? What if I put a little motor right here, connect up it, and connect the fan to it, and then run this at 60 hertz, right? And then I know exactly how much air I'm going to get, right? Yeah, that is called a TEBC. And the only difference is blower. So, here at F1 fans, if I got any F1 fans out here, like, so give me a cheer in the chat, because everybody knows if you're an F1 fan, when they come into the pits, like after qualifying, or they're putting them on the jacks or anything, they bring the little leaf blowers and like hook them into the engine, and that's what you're doing here, because on an F1 car, you've got all of this like high performance heat built up in the engine, and you're needing to get the air flowing through the radiator in order to get that heat out. And so they bring in these like leaf blowers and hook them into the intakes. Well, this is what a totally enclosed blower cooled motor does, is it takes a leaf blower and blows it on the motor. And I will go ahead and tell you, in a pinch, if your blower goes out, yes, a leaf blower will work, because yes, you can absolutely hook up a fan, an external fan, and keep a motor from overheating if your blower goes out. And it sounds crazy, but if you're having trouble with an overheating motor, in a pinch, you can just get more airflow over the motor, and you can kind of get out of trouble. I literally have a company that shall remain unnamed. I don't think anybody's in the chat from this company, so don't worry if anybody's on here. But I have literally seen one of these motors right here just have a air conditioning, like a small air conditioning unit blowing on it. Because if you notice, you see a fan anywhere on this? Nope, you don't. This is the encoder. This is just the body of the motor. So this is called a naturally cooled motor. So this motor, its rating, which whatever it is, it's not going to focus on it. But so whatever the rating for this motor is going to be rated for an ambient air temperature. In this case, let's see what it is. Wow. It's 155 degrees Fahrenheit, obviously. So it has an ambient rating. I may be wrong on that. That might be the winding. That's F-class insulation. So it is rated for, essentially, it's probably 130 degrees Fahrenheit, whatever that is in non-freedom units. Yeah. Somebody comment. What's 130 Fahrenheit in C? But it'll be rated at that temperature to be able to do its rated torque, which is based on current, remember? So like this down here, it's I squared. So this can dissipate so much heat at ambient air with zero airflow, because this does not have any sort of airflow. So this motor is actually, I think, yeah, it's IP64 rated. So it can actually have like splashes of water on this motor, and it's totally fine. Where a TEFC motor, you might not be able to do that. It's totally enclosed, fan cooled, but this is just naturally going to be cooling the ambient air. The cool thing about that customer is what they figured out is the rating for these motors, the windings, the insulation is a lot hotter than what I guess you can actually put these through from an ambient air temperature. So if you force cool a naturally cooled motor, you can increase the current out to it and it not overheat, it not burn up. And so we're going to talk about other cooling methods here in a second, because I'm going to go over to, and that is kind of a external chilled type system. They literally took a small portable air conditioner and had a little ducted airflow and ducted it over onto that motor, not that motor, but a motor very similar to that, and was just cooling the motor with that air conditioner. Pretty cool. Absolutely redneck engineering. It was in Alabama, Roll Tide, and yeah, I will never tell you where that was. But some of the cool things that they understood was that the rating of that current rating on that motor is just based off the cooling, and that basically it doesn't have any cooling. So I'm going to go now. We've talked about kind of motors that you will see a lot in kind of industry. You'll see these induction motors, these TEFC motors, and what most people call the servo motors, these guys. Now, obviously, I talked about this last session. This motor has to be controlled with servo control, but a better way of naming this motor is a permanent magnet motor. Okay, so the actual shaft on this has neodymium magnets on the actual rotor, and the windings are around the outside on the stator. So this is a permanent magnet motor, and so you have to keep up with where those the magnets are. So what's called a pole alignment. And so this is a permanent magnet synchronous motor. So this is a synchronous motor. Okay. We talked all about asynchronous stuff. So, but just know now we're talking about cooling. All right. So this is a natural cooling. So there's no fan, and in a pinch, you can do what's called forced cooling. So blower cooled forced cooling, or what they did at that unnamed plant somewhere in Alabama. They created what essentially is a chilled cooler type setup. And so what I want to show you is, I want to take you through the SIMOTICS catalog, which, if you are not familiar with the SIMOTICS catalog, you have a life. No, I'm joking. You may not have a life, but if you know the SIMOTICS catalog, you definitely weren't involved in the party scene. But Ali Reza, back. It's good to see you again. So yeah, I joke about this, but let's see. I want to go to the SIMOTICS, the D21.4 catalog. It is a wonderful one, and if I can get up here, maybe. Is that going to be the best one? Which one? Where do I need to be? Nah, I need to be on this side. So let's talk about this catalog. So this is the Sinamics S120 and SIMOTICS line. And this actually has quite some interesting motors in here. So we have talked about the servo motor lineup, the permanent magnet servo motors that we kind of talked about here. We have this main motor, and the 1PH8 motor, while it's in the Simotics line. It's in the motion control catalog because it's in here with the S120. You know, if it's in the same catalog with the S120, these motors mean business, right? So, but what I want to talk about is the fact that this 1PH8 motor is actually a special designed asynchronous induction motor. I mean, they do have synchronous version type, but this main motor here, asynchronous, okay. But I wanted to show you just, well, my head is blocking it, of course. I wanted to show you, if you could see here, you have forced ventilation options, okay, kind of like the TEBC option, blower cooled, but then you also have these other ones that are water cooled, okay. Oh yeah, so the music is it did hit right at the perfect time when we're talking about these awesome Simotics motors. But yeah, so the music is, by the way, I think I finally got it to where you can hear it, but all the beats are by my brother-in-law. Yeah, so got some talent throughout all the family. I wish I just had some. I'm joking. I will never have some. But we were talking about this water cooling. So water cooling is kind of like that redneck, a non-redneck version of what I was talking about before. Because water cooling actually goes through, and I wanted to see if they actually had a picture of it on here, which maybe they do here. Yeah, so here's a water cooled. Let's get this zoomed in. So with water cooling, you actually run water through the case, the housing of this unit, and the cooling capacity obviously at that point is rated at a certain input water temperature. So if you're able to cool that water to a lower degree, then you can actually cool that motor even more. So again, what it talks about here, like what it says here. So when developing the Simotics M1PH8 motor series, we place special emphasis on making them perfectly compatible with the S120 drive system. What's more, thanks to the harmonization of the system, they are capable of handling extreme duty cycles, short rise times, and exceptionally precise in terms of speed, torque, and positioning. All that to say, they can get really hot and take it. These things could take a beating. And the cool thing about it is, remember, the size of a motor really comes down to how much heat it can get rid of. Because the more current you can run through a motor, the square, so it's a square law, it goes up and increases heat in that motor by a square. So if you could get that heat out, then you can make motors smaller. You can make motors smaller and more powerful in the same footprint. So one of the cool things about the 1PH8 motor in particular is because they are blower cooled, they are rated at their rated power from 0 to rated speed without the asterisk on the 0. So you can sit there and hold 100% rated torque for all time S1 duty and have no problem. As long as that blower is going, it can hold torque. So these Simotic 1PH8 motors are really good in fan application, or not fan applications. If you put this on a fan, you're like buying the most expensive fan ever. On crane application, hoisting applications. So if you're sitting there holding torque on something, because like in a crane application, even if you close the brake, a lot of times you're still holding torque against the brake just to make sure that load doesn't fall. 1PH8 motors, they're designed for it. There's another motor in Europe and in kind of the European market. I think it's the 1FD, so Frank Delta. I think that those are also specific for crane duty motors, but they're just like the big brothers of these things. Hey, just don't put the clipboard in front of the fan, Lucid. That's what I'm telling you. Just don't put the clipboard in front of the fan, and you never have to know how much a replacement fan for a 1PH8 motor is. So for real, that is one thing. Maintenance on these things. Remember, all these blower cooled motors, they've got a TEFC motor turning the fan, or in this one's case, I think it's a naturally cooled motor, and so it's not like a fan in a fan. There's, oh gosh, which ones have I seen that are that way? Oh, the blower cooled. So there's like blower cooled 1SD, so like the SD 100s. So you can, oh, those are the XDs. There's a blower cooled, oh, no. It's like RZ something. Anyway, I'm getting off of it. Like there's a model of the SIMOTICS induction motor that has like its motor and then a small SD 100 like miniature SIMOTICS motor on the back of it. It's like a little baby blowing the blower. So it's pretty funny. But yeah, definitely on these, just remember that these blower motors are under the same rules of any motor. And I kind of joke around about with Lucid's don't put a clipboard in front of it. Your operators are going to find a way to mess something up. I promise you that. And so it's something as simple as having a system that's designed for airflow to come through. You put a clipboard on the outside of that thing, and you're like, oh, hey, this is this nice mesh metal little setup here. I'm just going to hang this clipboard here. That's going to be a perfect place for it. And then all of a sudden your motors are overheating and you're replacing $1,000 blower motors on 1PH8 motors. So there, little things like that can go a long way. But wanted to show you on this same footprint, water cooling. We're going to go through some of the torques on it. We're going to look at the shaft heights and look at how much torque is available on the same shaft height. And it's kind of sticky cool, but it's another thing you have to keep up with. Is like a chiller, water pump, circulation, and all of that. So let's take a look just really quick at these force ventilation kind of ratings. And again, the 1PH8, so Ali Rez is asking a question about an S120 card. That is a very good question. So, yes and no. So he's asking, is it possible to copy the compact flash card in a CU320 and use it? And part of the problem is the compact flash card has a secondary boot sector on it that is the bootloader for the CU320. And so if you were able to actually copy both partitions with a sector by sector image, like a direct image, you would be able to do that. However, that technically is violating the licensing agreement for the card. A better way to do it would be to, if you needed a backup copy of a card, yeah, so there absolutely is a way to do that with an image. I think there's like Etcher tool. There's a couple of like ISO tools that are able to do a sector by sector image of it. A better way to kind of play fair is to have a backup card, and you can load and make a backup of your program just by opening up with a standard compact flash card reader and going through and copying the files and the file structures into a folder. And as long as you don't have any like extra licenses that are keyed directly to that compact flash card, you can take that and go out and buy a blank compact flash card from Siemens, and just copy those files onto it, and it'll work, because that's the firmware. You just have to have the proper hardware bootloader on it. And so that's that secondary partition. So in all, yes, you can, but will I show you how to do it on here? Probably not, because I have friends at Siemens and I like to, but in a bind, here's the thing. If you're in a bind and you need a backup of a card, yeah, it's good to have it. So let's get back to these motors, and we have these 1pH8 motors. We have these 1pH8 motors, and let's just look at a speed rating on this of, say, 2500 RPM. So we have this shaft height 180 here, and it has a Newton meter rating of 298 Newton meters of torque. I'm gonna write this down. 298. And also, if you're using this, if this is the first time you've seen the PM, it's not PM, that's old school. It's the D21.4 catalog. In these 1pH8 motors, the line voltage is 400, and then it is saying for a smart and basic line module, you need to pick from this list. So if you are in Europe somewhere, so you're in Germany, you have a 400 volt line, and you are using a smart and basic line module, here is your ratings for like a 1500 RPM motor. Okay. If you just look at this shaft height 100 has 24 Newton meters of torque, and it has a up to 5,000 RPM before operating speed during feed beaconing max. So that is the actual maximum speed that you can get out of this motor, actually driving it. So that's what that N2 rating is there. So kind of go through this, and for us here in the US, we would have to keep scrolling down and find our 480 volt catalog. I'll go ahead and tell you, these are just the ratings. Remember, it's all a ratings game, right? So 480 volt, they assume if you're 480 volt that you're at 60 hertz. And so guess what? That's not a 1500 RPM motor anymore. That is a 2000 RPM motor. Okay, because it's base ratings. So let's look at that same shaft height 100 motor. Oh, it's running faster, right? 22 Newton meters of torque instead of 24. I do not yet, Ali Reza. I could probably, I might kind of look up that. And he's asking if we have a tutorial on how to erase and program an SMI. Are you talking about the integrated encoder on here? Because I have an extra one that I have scavenged off of that, and I would love to do that. That's like a fun one. So Ali Reza is asking about the built-in encoder on here. When it shows up in your project, it shows up as a signal module integrated, right? And so these are actually tied to firmware of a card. When you take these out, there's like a little board in them that's actually configured to these motors. And so that would definitely be a very good skill to have. Even though I think Siemens has, they'll do it for you. They'll send you a quote to do it for you. But yeah, I do have one. Maybe we'll do that at some point, Ali Reza. That you've got all the fun the fun stuff that I can't do on stream. But yeah, so back to the motors. We've got, if you notice, this is going to be that same motor. Okay, it's going to be the same rating, the same motor. It's just because of the different ratings, it's going to have a different part number. Okay, so a shaft height 100 there, and then the different lengths. So it's like a 101, 103, 105, 107. It's the same motor. It's just rated differently. And so, just so when you're going through this catalog, if you're looking at the different ratings, just make sure you're not looking at the wrong voltage rating. Okay? Yes, you can absolutely run a 480 volt rating in Europe, but you're not gonna get it out of a basic line module or a smart line module. You will have to go to where is it? It's an active line module, because active line module, you can boost the voltage up to whatever. And so these actually have higher torque ratings, just simply because they are on an active line module. So you can set, if you're using an active line module, you can set up a motor, even if you're in Europe, on a 480 volt line. And so you can use the 480 volt ratings. You get that extra torque out of it just because you're using an active line module. So, but they ain't cheap. But I love them. We just put an active line module in, actually, Lucid's plant, and I love it. But grounding, let's not talk about grounding. I'm traumatized by grounding. So yeah, so you kind of go through, and again, looking at this catalog, make sure that you are not only looking at the 480 volt. Here's the active line module. So we scroll on down, 480 volt active line module rating. Oh, look at that. It's got extra 2200. So depending on your line module, you have different ratings, which kind of makes sense. And if you notice on this, you're getting closer to the rating for the torque rating for the active line module for the other one, because it's bumping up that current. So one thing I wanted to show was, let's just look at this 1500 rating. So 1500 bottom, shaft height 100, that torque rating, same motor. This is just a water-cooled version, same frame size, same everything. This is just water-cooled version. It has, what is that, 30% more? Actually, no, that's 50% more torque, right? Because it was 20 something. And if we go down to our, what was that, our 2000 shaft height, oh, it doesn't even have a water-cooled version of it, but everything's more compact. So we had to go up to a shaft height 180 to get 300 foot-pounds of torque. This is 20 millimeters smaller or shorter. So considerable frame size difference just by going to water cooling, because you're not having to rely on whatever ambient air, or sorry, just air. You're actually forcing, just like a water cooled GPU in computer, you can overclock it. So overclocking your industrial motors, that sounds like fun, doesn't it? All right, so it is 7 o'clock. I have actually lasted longer on this than I thought I would be able to. I was tired. I don't know about you guys. It's been a long week. So I want to show you these guys, because these are a totally different ballpark of these things. So let's look at first, I want to show you the torque motors. And oh, they're so cool. So really these like 1FW6 and these 1FW3s. So I nerd out on these. Sorry. So these are kind of like these low inertia spindle motors. So like super high speed stuff here. So in these, you can't even really tell, but instead of having a shaft, this whole inner ring rotates. So you have the outer stator that you could bolt to something, and then you have you can have this like this whole inner ring is actually turning. Super cool applications, but all of these are water cooled, and so they are from the ground up designed to be water cooled because they are designed to be essentially a gearbox elimination device. So you put these on like a turntable, and you just have the motor clamped to the base, and then the whole turntable is on it. Yeah, and by the way, we have some celebrities in the chat with System Restored. They have a great channel too. My thoughts on the S200 series. So far, I have used the S210s, and I used them when they came out, and you want to compare them to like the V90s, and I have done a couple of projects in the V90s, and I guess this was before 2019, 2018 or whatever, when Trump Vector. So before the V90s in the US had that 25% tariff put on them, I didn't really see the point of the S210, honestly, because it was essentially the same form factor, the same all of that, and you didn't really get much more for the money. But now that in the US especially, the S210s aren't that much more than the V90s, there's no way you would catch me speccing a system with a V90, especially in the US. S210s, because it's all in Portal, got the technology objects native. Like, yeah, you can use technology objects with the V90. Honestly, I'm probably gonna do a V90 Delta picker here on the channel, and use the kinematics technology object and all of that. But for the price, you do get so much more for the same price if you're in the US. I have not used the new 220. I'm supposed to get a demo unit from our guys here down in the South to kind of play around with, but the integration of everything into Portal is well worth it if you're in Portal and you can afford the cost difference for the S200. They can do some pretty cool stuff at that small scale. If you're not familiar with the S200 line, they have, this is a I keep pulling this thing up. I'm gonna like throw my back out on it. So this is a 1FK7 servo motor. There is a 1FK2 version that is designed for these kind of small single axis applications, whereas these are kind of inherently designed for the S120 setup with your common DC bus. The 1FK2 still can get up into this kind of frame size here. I think this is a 40. Yeah, so this is a frame size or a shaft height 40. But you also have these much smaller, like shaft height 22, 30 range, so it's like smaller versions of this, the 1FK2s, and they are designed for the S200, so S210 and now the S220. And instead of having like a an encoder cable, and then, well, actually encoder cable and then a motor cable, they have this like kind of single one connection. You connect over to them, and you got everything in one. Pre-made cables for small systems like AGV actuators, things like that. They're really small. They're really compact. I really like them. So there's the 1FK2s are not in this because they are specific for the S200. So the G220, honestly, I just heard about the G220 just a few weeks ago, and I kind of like asked my motion specialist, like Siemens motion specialist, I'm like, why? And they were like, it's got new features. And I'm like, okay, cool. So G220, the S220, gonna kind of get my hands on some of those and maybe do a live stream on those. I may try to do it with our local distributor. I say local. I live in Atlanta, and this is kind of like hard. I worked for electrical distributor in Birmingham, Alabama, which is, if you're not in the U.S., then you have no idea what I'm talking about, and that's okay. But S2, okay, yeah. So that definitely is something that is something there. So the redundancy on the G220. So yeah. So part of the problem is I've worked for almost 10 years as an application engineer at electrical distributor in Alabama, and I now live in Atlanta, but my company is in Alabama, and so we buy everything from Alabama. And so all my local guys here in Atlanta, I don't waste their time because I don't buy from them. and so it's like I literally could almost see the Atlanta Siemens electrical distributor, like motion distributor, right up the road here, and they're really good. But I buy all my stuff from where I used to work, and so I have to plan a little bit more in order to do like live streams and stuff, because I respect the guys here in Atlanta enough to not waste their time if I'm going to be buying out of Birmingham. But yeah, I definitely plan on getting a G220, S220, and play around with those. What might be pretty cool is if I get this Delta picker, if I could get a hold of three of the S220, just kind of like maybe samples or something. Maybe I can wheel and deal with something to be able to compare the process between a V90 and an S220. I think that would be pretty cool. Yeah, these linear or the torque motors here, I've only ever had one application that I've been able to do it, and it was a centrifuge application, and it was stinking just cool. Yeah, so I have some V90s that like I missed I missed size. Hey, thank you, System, for being on. It was awesome seeing you, and good luck to your channel. Y'all look up System Sword's channel too. It's got a bunch of stuff, a lot of different, probably a little bit more varied automation information than I do. I'm pretty heavy Siemens, but yeah, you can find them on LinkedIn as well. That's where we got hooked up. So it's good to see you. I hope y'all have a great weekend too. But yeah, talking about these 1FW motors, they are incredibly high torque for what they have. So like the maximum torque here, 34 Newton meters, and this is on a I can't remember the frame size on this. This is like a very small, and it's 34 Newton meters of torque, and they can get up kind of stupid high. And this is with natural cooling. I just noticed that this is natural cooling. With the water cooling, it kind of gets up even more. So a little bit about these, just pay attention to the rating. And so like very, very cool stuff here. The last motor that I want to talk about is the linear motors. And these are some of the ones that you don't really see a lot out in the wild, but you tend to see a lot in, I don't know, a lot of cool stuff, because these are actually, let's see if there's a good, here's a good picture. Oh, welcome, Ignatius, like Ghana. I have some friends that are from Ghana, so like that's awesome. I love, again, I just absolutely love the international crowd you get with working with this. And welcome to the stream. It's great to see you. Hopefully all this stuff, like you said, is great to you. Hope you subscribe. And yeah, if this is your first time on stream, welcome to the stream. If you're watching it on demand, if this sort of stuff interests you and it's helpful, I try to do these every week, a live stream every week. I've gotten behind on putting out edited content, but I do like to have some edited content, but I've been really, really busy. So I appreciate everyone that joins live. It's so awesome to see everybody chatting it up and talking. So yeah, so these what's it called? The linear motors, they're so cool because I've been talking this entire time about rotating magnetic fields. Well, these are fixed magnetic fields, and so essentially you put a long strip of magnets, and so let me clear this. I'm gonna swap over because these things I want to page fit here. And I'm gonna pull this down here, and we're gonna go down to my sketch pad, and we're gonna talk about these because like it's pretty cool to because this is just like a bunch of like magnets sections, right? So you can kind of see them here, like a bunch of little magnets, right? And what this does is built in with a linear encoder. You actually have these coils that are built in to these primary sections. Oh, New Year holidays. So, dude, that's awesome. It's 2:40 in the morning. So, all right, I've gotta give props to Ali Reza for being on the channel, on stream at 2:40 in the morning, learning about some awesome Siemens drives, and New Year's holidays. That's pretty cool. That is awesome. Like, I feel honored that as you're celebrating all of this, you choose to celebrate with knowledge. But yeah, these kind of fixed sections are magnets all on here, and then the same kind of technology is it will kind of pulse these signals as it's going along in order to move this down the track back and forth. Super cool applications on this. There was like there was an inverted pendulum application with this that yeah, it's just super cool. If this is a type of application that you think you could see like really precise linear motion, these are not cheap. I'll put it that way. They are definitely not cheap, and you definitely need someone that is experienced from Siemens in specifying these to actually specify one of these systems, because they are cool, they are precise, and they are expensive, but they are awesome. But yeah, so that's kind of like your general like spectrum of motors. And honestly, I thought that was going to take like 30 minutes to talk through, and it talked through I mean, it's only been 2 hours. It's only been 2 hours. So I want to show you something though, that I'm gonna give you a little secret here, and that'll take Ali Reza into his New Year's celebrations, and maybe this will be the last thing that he could stay awake for tonight. But yeah, so just cheers to Ali Reza, everybody in chat for that. But we've got a manual that's down here right now. I'm gonna clear this out, and I'm gonna swap over to this guy. And anybody that, what page am I on? I have to remember, 172. Anybody that is like, I don't know, worked with Siemens drives and motors for very long knows about this, and knows that it is the secret to all things Siemens drives. Okay, and this is my gift to you, the Synamics Low Voltage Engineering Manual. All right, and I kind of get nerded out on this thing because I've been kind of like pulling most of the stuff from catalogs, and there's a lot of information in catalogs about different ratings, about different systems, about all these different things. But the engineering manual is literally how the engineers designed the system. So how they actually designed the hardware that you were using. And it has some of the most deep information you have about these drives. If you were kind of like in that like upper level of in your career, or you're really wanting to like dig into how to really maximize these drive systems, especially if you're doing high powered drives, this is the manual. You have to have this manual. I'm going to throw this manual over into chat, or at least I think I will. Maybe not. I had it. I'm gonna have to find it again and send it out. Y'all all know the do this. Come on. I had a window open here. Support. And then I'll get this here in a second. But yeah, this is somehow, wait a second. I have it open. I have it open here. I actually prepared for this because I was super excited about sharing this with you guys. Because affectionately, I know if you're watching this stream, you're a nerd like me. We understand each other. And so this guy right here is your lifesaver. It is the engineering manual. Ever done a MicroMaster migration? Oh yeah. Yes, MicroMaster. I've done many MicroMaster migrations when they went. So I guess their product life cycle. So their PLM like 500 now. So they are in non-production for the MicroMasters, or at least in the US. And yeah, cool thing about it though is the IO layout for a MicroMaster 440 is the same IO layout for a CU240E, just so you know. So if you change over to a CU240E, you do not have to change your numbering on your drawings. So yeah, MicroMasters, I've done those, and yeah, they've been like, all right. While we're on this, hold on, we're gonna do this. Sorry, you got me pleasantly distracted. Because, all right, where's my, no, this one. We're gonna look something up real quick. I want to see something. I don't think I have a part number, or yeah, I want to see what what life cycle this was. So, intentional. This product was canceled on October 1st of 2019. So if you and this is the 440, this was the 420s and the 430s were canceled before, well before that. So if you were just now migrating 5 years, and product cancellation means they're out of full serial production. If you're just now cancel or upgrading your MicroMaster 440, we have a term down in the South. Bless your heart. That's what I will say, because the final product, so they will not support at all this product in 2027. So you got 3 years before, like right now you're probably paying, oh gosh, it was like triple back in 2021. And that was not the whole COVID pricing. So yeah. Anyway, this product was released in 2002. Okay. I mean, it has literally been around for 22 years. Obviously, it is a really great product. So fun fact. G130, completely current product. Okay. G130 is a MicroMaster chassis. I'm not lying. It is literally a MicroMaster chassis unit with a CU320 running the hardware. So these are some good drives, and I can guarantee you that somewhere out there, there is some piece of equipment that someone has not opened up the panel in 20 years. And it has a MicroMaster in it. And they're going to go into it and be like, how do I get this? This is a 5 horsepower drive. I need a replacement for it. And they go, and that 5 horsepower drive is going to be like, I bet you it's at least $3,000. I bet you it's at least $3,000. So this is a 1.5 kW. Let's see. I bet you I don't even have list pricing on this. Let's do this. Let's see what the list price, if it even has a list price on it. Yes. If you see one of these, oh, sorry. I don't know if y'all can see that. List price is $2,800 for a 1.5 kW drive. So, yes, slowly, gently. Oh, but there is international stock on them. Yeah, so go ahead. Yes. So let's see what the list price is on a comparably sized PM240 or a comparably sized converter in a G120C. Not that. It's hard for me to see. Standard performance, G120C. And this will be, let's just see. So 1.5 kW. So the way they're rated, it's going to be that. Actually, no, these are rated the same. That's wrong. Did that wrong. 1.5 kW. Because G120Cs are rated, and we're going to talk about ratings here in a second. I'm glad I told I'm glad I told my wife to eat without me. All right, so version. So let's just do a Profi.net version. All right, so that one's 1,000. So let's do the actual version, since you would have to the USS version. So yeah, so $800. So I don't know. So a $900 list price drive. That's your replacement right there for that drive. If you need a Profibus, it's a little bit more. Ethernet, a little bit more. But yeah, so $900 or $2,800 list price. Obviously, you get a discount off of that, but I can guarantee you that $2,800, you're not going to get much of a discount off of that. So anyway, a little rant there. I also fully understand the pain of upgrades. Like, don't get me wrong, fully understand the pain of upgrades. And so, like, the upgrades that we did, the biggest problem was that the facility that we were doing these MicroMaster upgrades in was a FDA regulated facility. And so any changes had to be FDA approved, regulated. They had to submit all of this paperwork and all of this stuff. And so it was an absolute pain. And so they did not want to do it. And so I get it. I get it. But the IO on these are pin for pin, terminal for terminal, the same as a MicroMaster. So yeah, just there. All right, I'm gonna go back to my cool other nerd stuff. So yeah, engineering manual. Thanks for the thing about the MicroMaster there. Cheers on that. Which, that is some good not water. All right, let's go back. Let's go back down to this guy. I want to go down to Sketchpad. This. We're going to talk about this. This is the engineering manual, right? The coolest document. Obviously, just the sheer number of things on it. Any sort of like technical information that you need about Siemens drives, it's in here. What I wanted to do is talk to you about low duty cycles, okay? Because this is how drives blow up or don't blow up. And there's also some other things too, like capacitor forming. That's in here too, as well. But so Ollie Reza's got an interesting question. Is it true that Simotion D is dying and will be replaced by the Dynamics drive controller? I don't think so. Like, because here's why. The Simotion D they would have to come out with a new version of the Simotion D, put it that way, because the Simatic drive controller is just a 1500 or a 1515T processor, and the performance of the Simatic drive controller is not that of the Simotion D. It's just you just can't. It's just not quite apples to apples comparison. Now, maybe with an upgraded hardware version of the Simatic drive controller, maybe. But the one that I looked at, because I did look at a Simatic drive controller and I have done some Simotion D projects as well, the performance levels weren't quite there on the number of axis counts that the Simotion D. So like a 445, like a D445, I think has like 128 axis count. And the highest level control on like the original drive controller, it was like 32 or 64 or something like that. And at that same performance level. And so printing presses, I don't think you would be able to do a printing press with a SIMOTIC drive controller. And I could be totally wrong. And hey, if you're watching this on demand, Siemens drive people, tell me I'm wrong. Tell me I'm wrong, because I'd love to. I use the 1515T processor. That is my, if it's not a low-end project, I use the 1515TF. And so I'm pretty familiar with the performance level of the 1515TF. And so it's good, but it's not Simotion D. It's not Simotion D level good. So if you're not familiar with there's a product called the SIMOTIC drive controller that has a 1515 or a 1500T processor, depending on what version, and a built-in CU320-2 control unit. And so you can take oh, okay. So yeah, so the like, so System Restore, wow, just only six interpolated. So that's, yeah, the performance level is definitely way off. I know that you can do, we're kind of getting off into the into the world of processors and everything, but it's good to have people just like chat and stuff on this, because I have a project, a winder project right now that's running more than 6 axis on a 1515, and that's only on a 4 millisecond servo cycle time. And so I don't know if Lucid is still in here. He has that same 1515T processor running in his plant, and I want to say I think he's got 12 axis, but I don't think they're all synchronous motion. So obviously I've talked about this in other streams about the technology objects. Yeah, so 14. So on a 1515. But and what's your servo cycle? Yeah, so kinematics are very high, and that's, yeah. So kinematics suck up a lot of motion resources. And so yeah, and Lucid, what was your servo cycle on that? Was that a 4 millisecond servo cycle? Now your yeah, motion control charts is, yeah. So kind of got a couple different conversations, but yeah, so like the drive controller, and it is designed for technology objects. So kind of a lot of the stuff that's on my channel, I have a lot of different ways of using technology objects, just because it is a super easy way to gain entry into motion control. And it is, the SIMOTIC drive controller is great for that. If essentially you have like a Cartesian picker or a Delta picker or something like this. Oh shoot, you're just giving me ideas. Yeah, don't make me spend money on a drive controller to do my Delta picker with. I have 1515Ts at our shop. But anyway, the kinematics suck up a lot of those motion resources, and for like position, I can't remember the breakdown of them, but yeah, with a kinematics you have to have for every axis that you are running. So for 6 kinematics, you would be able to run 2 Delta pickers on a what's it called? On a 1518 TF. So in those sorts of worlds where you're getting into like robotics and kinematics, the SINumeric controller is the same controller as the Simotion D. And I want to say it can run like 4 channels of like 8 axis of motion. So you're talking about twice as powerful as the most powerful 1515 or 1500 TF processor. So it is that the D, that Simotion D processor, it's old. It's a 400 controller. Like, I mean, it is not actually, I don't even know if it's a 400. I think it might be like a 317 or something like that. But it is highly optimized for these type applications. I don't think they'll be able to get away with it. You have to be able to replace the technology, especially Siemens, because Siemens wants to be the highest performance. They want to be the company that does the cool stuff. And so right now the drive controller just doesn't. MCCs, if you're not familiar with the Simotion or SIMotion or C-Motion, it's supposed to be Siemens Motion Platform, whatever. Anyway, there's 3 ways that you could program motion control in that C-Motion D platform. There's one with the worst ladder logic editor you have ever experienced in your life. Don't ever try to use ladder in Simotion. Then there's ST, which is similar to the SCL that I'll use every now and then in some of my stuff. It's very similar. So it's structured text. It's like Fortran or something based. I mean, it's a text-based programming language. That's what most people use. But there's this a programming environment called MCCs, motion control charts. I guess you have DCCs too, so there's 4. That motion control charts are the easiest way to do motion in a SIMotion platform. It just has like your different states. It's like you create a state machine and it goes through it. I agree, Alireza. ST is, if you are coming into a SIMotion platform and you kind of need to have the mentality of high level programming, that an ST just works so much better at it. And that's why you'll see, like, I don't know if I'll ever have these on streams. I have done a stream where I've done SCL. It is very similar to ST. It does like math and processing because it's like C++ or C#. I mean, it's a text-based language. But yeah, I don't know if they'll have to improve the drive controller a lot, because it's just not there yet. Because the drive controller is based around technology objects, and they're not as optimized for performance. They are optimized for ease of access. So yeah. So go back to which, by the way, I'm perfectly fine with hanging out and just talking about random stuff. And so, like, this is fun. It's nice to have people that are on interacting in chat. This is kind of what I would love to have all the time. Most of the time, I have these during the day, so that people can. My thought would be to watch them on their lunch break or whatever, because that's honestly when most of my viewers are online or around lunch in the US. And so, but yeah, it's fun sitting talking nerd stuff on a Friday night to people that are celebrating New Year in on the other side of the planet. I can't remember where Ali Rezi was from. I think it was from, yeah. But yeah. Anyway, all that to say, talking about, I'm gonna spill the secret sauce about, yeah, Iran. And that's what I thought. I didn't want to misspeak because someone had said something about Turkey a little while ago. But yeah, I remember now, Iran. So yeah, awesome. And so, yeah, so I'm gonna spill the sauce on if you've ever experienced other brands of drive. Okay. Yeah. But yeah, if you've ever experienced other brands of drives that maybe didn't have the level of reliability that you would expect from a Siemens drive, I will not name any other drives. I will just talk about Siemens drives, okay? I will say that if you go into two of the toughest places in the US to have work, that's coal mines and steel mills. And those are the worst, like mining and steel mills, metallurgy, those are the hardest on equipment. You will see two brands, or you'll see a lot of spares, put it that way. You'll see a non-productive plant if you don't see one of these two brands, put it that way. Hush, we're not talking about any other, we're not bashing anybody, but you'll see one of two brands, and that's Siemens and ABB. So the Swedish, that like they got their stuff together, they understand stuff, and so like I cannot knock ABB drives because they're good. I have a ton of experience with Siemens drives, and so I kind of like don't have any experience or a very much practical experience with maintaining other brand drives. I started repairing Siemens master drives when I was about 14, and so they've been around the block and like come through all sorts of stuff. But all that to say, I never really understood the actual difference. Okay, so the actual difference of why one brand would when you're buying like a 100 horsepower drive, and we'll use, if you're buying a 100 horsepower drive, and why does one brand's drive seem to last so much longer than another brand's drive? Why is that? Well, obviously there's component quality, like QC, like all of that stuff. There's age of components, especially like capacitor forming. If you have a drive, and I'll go ahead and say this, if you have a drive that has been on your shelf for more than a year and a half, because it most likely was produced, sent to you, and has sat on the shelf, and from production to the time that you're looking at it is probably about 2 years if it's been on your shelf for about a year and a half. The likelihood of when you throw power on that drive, and that this is not brand specific, this is anybody's drive, the likelihood of it turning into letting just all of the magic smoke out, and if it's a big drive, blowing the door across the room, is non-zero. Any drive, including Siemens, because if you let capacitors sit without voltage on them, these big dielectric capacitors that look like my tumbler here, they physically start to degrade. The dielectric in them physically start to degrade, and when you put voltage on them, they have incredibly high leakage currents. And so there is a process called capacitor forming that every drive manufacturer has to do. If you have a VFD that has been sitting on your shelf for more than a year and a half, you need to be thinking about forming the capacitors on it, any size, especially big ones. The bigger it is, the more you got to worry about it. And so part of that description is here in this manual of how to do it. Essentially, you're taking and putting low levels of voltage on it and then just kind of letting it simmer and then slowly building up that voltage. Now, Alpha, we've designed a device to where you plug this device into the wall and it actually just like forms the capacitors for you. But most people, there's all sorts of different ways you can do it, but there is descriptions here in this this manual of how to do that capacitor forming. We're not going to go into it now, but you absolutely need to do it. One thing though that I do want to talk about is like what actually makes a drive different between like different versions of drives, even in a manufacturer, and a lot of it comes down to the rating of the drive, right? Well, I'm buying a 100 horsepower drive; they're all rated the same, right? No. Remember, we talked about before about your enemy and what you were fighting on a rating and in your system is heat. Okay, so you need to be building up or getting rid of heat. And so one of the ways that all drive manufacturers rate their drives is based on either high overload or heavy duty or light duty or low overload. Siemens World, it's high overload, low overload. Other American manufacturers will say heavy duty, light duty. Okay. I will go through just talking about what is actually kind of going on with this. So I'm going to get this a little bit bigger so y'all can see. So this is a I love Kentucky. Just saying. And that's a hint about what's in my tumbler. But so what we're talking about today on here, these low duty cycles defining high duty or high overload, heavy duty, low overload, light duty. Okay. You'll see these little curves and you're probably familiar with this. If you've ever bought a drive, if you've ever gone through something, you see, that, all right, this is the low and this is the high. Okay. And a drive will be rated. So say you have 100 horsepower, low overload, and then that same part number will be rated 75 horsepower, high overload. What the heck does that mean? Well, obviously it's derating something based on the amount of heat that it takes, because it is all based on these duty cycles. And I talked about duty cycles earlier, and I mentioned S1 duty cycle. S1 is continuous duty. So you are running at just constant duty. Okay. Well, if you notice here in Siemens, that rated current, so I rated, is the same. So we are looking at this same drive. Okay. So this converter current, whatever it is, it could be a 10 amp drive, whatever. This part number is the same on both of these guys. Okay. One thing to note is that Siemens drives are always rated on current, and that is not the same for other manufacturers, because Siemens will give you these numbers, but it's just a suggestion, or, oh, hey, this covers a standard 75 horsepower motor, right? Well, we're going to talk about the reason why you always need to do it on, or it is better to always base it on current. So here we have our I rated. That is the continuous duty current. Say that's 100 amps. Okay. That's no overload. It can run 100 amps all day, every day, possibly forever. I mean, not really, but for as long as the life of the drive is. That's I rated. Okay. So you have this this IL and then an IH, which is the, over here, high and low currents. And essentially what this is in order to not build up heat, because heat is based on I squared T, we talked about that before, every 300 seconds, so 5 minutes, if you follow the low overload rating, you get, if this low overload rating was 100 amps, then you would get to run up to 110 amps for 1 minute, so 60 seconds, and then you would have to go down below your IL, low overload rating, for the rest of that 5 minutes. So for the other 240 seconds, you would have to be down at this IL rating. Okay, if you notice, IL is below, IL's down here, and it's below the actual continuous duty rating because you're using up some of this thermal capacity. So this thermal capacity here gets restored in this thermal capacity here. Okay? Pretty cool, right? Well, there's this other rating, the high heavy duty rating, okay? And it does this, it gives you, this only gives you 110 amps. We're going to say the same ratings, okay? If this was 100 amps, I rated, this rating, you would be able to actually run 150 amps, so 50% more current for that 60 seconds. Okay? And so you use up all this heat. Oops. So you use up all this heat above your I rated, so your 100 amps. And then you have to go below and give it all back. Okay? So it's this exchange. All right? And so that's what these ratings are doing. And most manufacturers are just saying, hey, you got your 110%, that's your light duty, and then you got your 150%, right? And almost every drive manufacturer will have this exact same thing, and it looks exactly the same. And so you'll have your low is a 110% overload, and your high is a 150% overload, okay? And so you're like, all right, everybody's the same, right? Everybody's the same. Well, guess what? Everybody's not the same. Because remember, I told you, everybody has this like 110 for 60 seconds, 150 for 60 seconds. Everybody has that. But guess what? I have not seen another manufacturer do on a 5-minute cycle. Everybody else's, it's a 600. So it is a 10-minute. It is a 10-minute cycle. And so you're like, oh, you get 60 seconds of overload, just like everybody else, right? Well, those other guys shall remain unnamed. You get 60 seconds every 10 minutes. Here, you get 60 seconds every 5 minutes. So inherently built in right in front of your nose, you realize that that heavy duty and high overload rating is not the same. Because what happens is this actually is twice the thermal capacity as the other guy. So a 300 second duty cycle, you taking 60 seconds of that on a 300 second shows that you actually have twice the thermal capacity of other brands that are on a 600, because you're still I squared T is the same, but the 600 second takes you twice as long to cool off. And most people don't actually use this type of like mentality. They'll use kind of a little bit of overload and then not quite a lot, and then a little bit of overload, not quite, a little bit of overload, not quite. And while it may not ever trip out on like I squared T overload, the fact that a Siemens drive has twice the thermal capacity means that it's wearing out just a little bit less every time. That means that even though it says that it's 100 horsepower, it means you've got a little bit extra, a little bit. You have double the kind of robustness of a 600 duty cycle. And that means that if that cabinet actually gets a little bit hotter and you're still only using this much and you're rated on your high overload, we're going to see here in a second that you derate based on ambient temperature, because hey, if the air is hot, you can't cool as much, right? Crazy thing too is if you're at higher elevations, you have to derate as well too, because there's technically not as many air molecules to grab that heat off of the cooling. And so say for example, in Denver, if you're at a plant in Denver in the US, you're at a mile up in the elevation. And I mean, I used to live there, and so I know you can feel it, and it doesn't seem like it's that high, but it absolutely is. Drives have to be rated basically a size larger in Denver than here in Alabama. Same motor, same process. If I send a machine to Denver, in order for it to perform properly, I have to size the drives up basically one frame size. So that's just kind of a little hidden thing about how this is rated. Well, cool thing about Siemens is in this manual, they don't just give you this type of rating, because these are sophisticated. This is an engineering manual, and you're an engineer. They actually go through and tell you, hey, explain to you all of this thermal capacity and periodic load duty cycles. Like I'll just read a little bit of this. All right. So this is how cool this is. This is an actual engineering document, an actual textbook. This is not a catalog. So like, for example, in the case of periodic low duty cycles, the magnitude and or frequency of variations in the IGBT chip temperatures must be limited during the low duty cycle in order to prevent premature failure of the power units. Would you listen to that? Premature failure. It's almost like if these things get too hot, they fail quicker. This is necessary because the number of permissible temperature cycles of an IGBT is limited and is further reduced as the temperature swing delta T chip increases. The lifetime of the IGBT therefore decreases according to the proportion of the rise of the temperature swings in delta T chip as described. As you can see, there's a lot of information in here. This is an actual engineering document. So we scroll a little bit down and they actually start to go into how they have determined that these cycles and how they determine the thermal capacity of it. And they are transparent in this. Show me someone else. Hey, I'm challenging anyone else, any other brand. Show me a document that goes into this sort of detail. I would love to see it, because This is actually like kind of like all the fancy stuff that like I tell you like on this, a lot of it just comes from some of these documents. So here's kind of like this derating factor, because what you essentially have is the short term time, or the short time current must be limited to values less than 1.5 derating factor times the current I. So it goes through all of these types of like how these things are rated. And you have these like pulse derating, temperature derating, parallel module derating, and then IGBT derating. So like all of this stuff is in here. But one of the things that I wanted to show you, just tons of cool stuff. You get down here. This is, not everybody goes bang 150% down to like IL current and then sits there for 600 or the 240 seconds. 150%, 240 seconds. Not everybody does that. It's usually, like I said, 110, 120 for like a second or two, and then back down, and then up and down and up and down. Well, here is the actual calculus. So this is the integral equation of that they use to, if for any like current utilization curve. So if your process has got currents that are going all over it, and you can fit a curve to it and put it into this equation, there you go. So that I squared T value, the heat value, the measurement of heat, there's your integral. So break it down a little bit between calculus and catalog. They give you this nice little practical method here. And it is super cool because most of the time you're going to have like a period. You're going to have a period of to where you're running basically around like the I rated value. Okay. So this here, I'll show you. So like I rated is up here. Normally you're going to be running somewhere down here, and then it's going to come up and then come down, and it's going to look something like this, right? Then it's going to come way down here, and it's going to look something like that. Like that's just random. Whereas your I rated value is like here, right? And we talked about this. If you're below the line, you're giving the heat back. You're building up heat, giving it back, building up, giving it back, etc., 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 right? Well, this little equation here tells you how to actually calculate that heat, so you can know absolutely 100% if changes that you're making are like in your load is going to completely wreck your process. Okay. So this is just a ratio of the current during some period of time. So the current during some period of time, and then you have this derating factor that it kind of talks about up there. So it's a ratio squared times your current of your period of time. And then you're just going through and literally adding up all of these, where the sum of all of these periods of time is not, or the sum of all of those is equal to this. And then there's this like, you want it to be below 300 seconds. So you want to try to do this calculation in a period below 300 seconds. Okay. So it's pretty cool because in that kind of period to where you have kind of these ups and downs like this, then you just take the current, say the average current during this time period. Okay. Then the average current during this time period. And then average current during this time period. Right? And then if this is your, like that, and you just put it into this. And so you can have as many periods as you want on this. But again, this is actually how these things are rated, okay? And so it's based on the heat. And last thing I wanted to show y'all was a couple of differences between, this is the freeform kind of version. And in general, this right here, so literally if you did a G120, a G130, this is going to be the overload rating, like kind of how the high overload and low overload works, okay? And this is standard, but just remember, this is on 300 seconds, so it has twice the thermal capacity as 600 second duty cycles. So let's look and compare this to a couple of other things. So, what page? So I told you that was the G120. Let's look at the S120. This should be on 128. Ha! See, I do prepare for these things. So here's a couple of different things about the way the S120 is actually rated. So this is for single motor modules in book size compact form. It's the same thing for the book size. Let's do book size regular, because they have like CEDs. So this is the C, and then this is the D. So let's just take a look real quick about how the S120 book size modules have a little bit different of a rating. And so they play with these numbers a little bit different. Okay. So on this, you were looking at your I rated value can have its I rated value can have a peak I max value. Okay. So a peak I max value for a quarter of a second every 10 seconds. Okay. Pretty simple. That's kind of crazy. So like you can sit there and built in the I max is a lot higher. And so it can have these pulses of just like pulses periodically every 10 seconds, a quarter of a second. And so you can start to look at those periods and say, hey, that's actually a pretty good bit of power there, you know? And so they also give you these other ratings. So they give you like the IH ratings, and then you have like your I rated things. But I welcome you to go through and look at this catalog. This is in the PM21 catalog that I looked at. But if you notice, there is what is called the what they call let me scroll down with this. So S6, all right? I love the S6 rating, okay? Because if you rate an S120 book size module on the S6 rating, it is going to be like, it's going to be the most robust style rating, okay? So figure out your current, and it is 0.7 times I rated is going to be your S6 rating. And so like, and what you can do is you can hit an S6 rating. So the S6 rating would be the maximum you would ever want to achieve. And you can run that current for 4 minutes out of 10 minutes. And remember, it's the same sort of setup that you have with that I showed you in the engineering manual, where you can kind of do, if you don't go a full 4 minutes, but on a 10-minute cycle, just get this, the S6 rating, that's 600 seconds. Everybody else is rating their stuff on S6, okay? So the S6 rating has 4 times the time that you can run the S6 rating than a high overload, for example. Same duty cycle. So the S6 is an incredible way to just kind of build in your rating. And I'll kind of show you. We could go into it, but I mean, I've already been doing this for 3 hours. Wow, that's crazy. But the S120, I'm going to show you the S120 book size, motor modules. Let's go into these. And I'll show you an example of this. So like this 45 amp rated device, okay? So you say, okay, that's the I rated, all right? Well, the S6 amperage for that device is 60 amps. So every 10 minutes, this thing could get bogged down and run 60 amps for 4 minutes long. That's kind of crazy. And so the IH rating is, again, that is how much you can do the whole 150% sort of thing. But you look at the S rating, that's probably, the S6 rating, that's probably a little bit closer than what you would think of, like, oh, hey, if I'm basing this off of, I have a 10 horsepower drive, okay? 10 horsepower drive, that's what, 14 amps, whatever. 10 horsepower drive, 10 horsepower motor, 14 amps, ballpark. Okay, so bam, rated, right? So our rated current 18 amps, so that's what we're going for, right? Well, our S6 duty means that 14 amps, you can do 200% on that motor. All right. Now, whether or not you're going to burn up your motor, totally different question. All right. But this drive can do a C-type drive on that S6 duty cycle can do 200 or almost 200% for 4 minutes over a 10-minute duty cycle. So that's how you kind of like look at the driving, size driving. So if you put one of these book size motor modules in and you look at the rated current of your actual motor and you cover that with the rated current you are actually pretty well protecting yourself. You have a ton of thermal capacity in there. We've talked about the G120. I want to show you though the G120X drive, because it is very important if you are considering a G120X drive, because it is not the same as a G120 according to the rating. Okay, let's look at this, at these ratings. Okay, so the high overload rating is, guess what? Why did it do that? It's 600 seconds. So the G120X high overload rating is on a 600 second duty cycle, whereas the G120, the regular G120, the high overload is on a 300 second. So still the same 110% kind of stuff, but it is very important that you know that if you're using a G120X, that their ratings are more in line with other manufacturers. So a high overload G120X will not have the same heat capacity as a high overload G120 just regular. So if you have like a 400 horsepower, or I guess it would be a 350 horsepower G120, just a regular G120, so a PM21.4 that goes up to 350 horsepower high overload, or maybe it's 300 horsepower. But if you have that same high overload rating in a G120X and you're like, oh, hey, it's cheaper. There's a reason it's cheaper. because it's less thermal capacity. And so what blows my mind is how, especially in these higher horsepower ranges, these other manufacturers are much more expensive than a G120. And like if you size them on a heavy duty rating, the high overload heavy duty rating, and you're going to pay considerably more for the other guy, and they are going to have half the thermal capacity. It blows my mind. So just pay attention, no matter what brand you are looking at, pay attention to these overload ratings, because that right there is what is going to determine how long that drive will last. So one thing that also degrades the life of a drive, and it talks about it in here, is this pulse frequency. Well, some manufacturers have made the decision on some of their product lines, not naming any names, to increase the default pulse frequency of their drive so that you don't hear it. And that inherently decreases the life of the drive. It also increases noise on your cable. That's why some manufacturers will absolutely require you to have a shielded cable, VFD cable, which pulse frequency causes more circulating currents. So you start piling up all of these things from an engineering perspective. And look at this document. It might be good to solve, it might be a good cure for insomnia, but this document is incredibly, there's a ton of information about this document, and I'll put it in the description. But man, it's been fun tonight. I'm not gonna lie. It's been fun. I didn't think that this topic was going to really end up being able to like kind of take the time that it has. And it's good that like everybody that's been on has been on, and like it's great seeing returning faces and kind of some like other people that are in the industry and kind of doing this content. I love it. And yeah, have a good weekend, everyone. It's been great. It's been great like learning about this stuff. It's been fun. It's always fun for me to make these sorts of things, to be able to go back and kind of like challenge myself and do this, because I mean, why do we really do any of this stuff? I mean, well, I guess making money, like paying bills, but I like to have fun while paying bills personally. But yeah, it's been great. If you have made it this far, thank you so much. Be sure to, if you've made it this far, bless you. I mean, if you're not subscribed and you're still here at this point, definitely hit that subscribe button. If you're watching this on demand, like, yeah, definitely look at all the rest of the content on here. It's been great. It has been, again, fun. I hope y'all have a great weekend. I will probably, I don't know. It's going to be a minute before I'm going to be able to get another stream, most likely. It's probably I'm not going to be able to do Monday, and I'm going to be traveling all next week. So it'll probably be almost 2 weeks before I get to do another stream. But no matter what, y'all keep learning and drop comments, ask questions. And Ollie, rather, you're still on. My goodness, do you not sleep? That's crazy. I'm probably going to be up for a while, but I got to go get something to eat. I realized that I've just had like a handful of cashews all day and I'm kind of hurting, but y'all have a good weekend. Y'all go out and do something fun. I mean, we got plenty of this like during the week to come back to it. So yeah, y'all peace out. Y'all have a good evening, good weekend. Take it easy.